Hello, I'm Bendong, a PhD student from University of Connecticut. My presentation today is about interpretable data-driven probabilistic persistent load margin assessment with uncertain renewable energy and loads. With the increased penetration of stochastic renewable generations and flexible load-induced uncertainties, there is an increased concern for quantifying system stability under uncertainties. If these uncertainties are ignored, inappropriate actions may be taken, leading to power system instability, like static voltage stability. Therefore, this work is focused on the probability load margin assessment. For the probabilistic load margin assessment or the voltage stability assessment, here these two have the same meanings due to the stochasticity and uncertainty from renewable energy and the flexible load. The load margin is not a deterministic value. Since model-based solutions are computationally prohibitive with the continuation power flow calculation, we try to use data-driven methods to solve this problem. However, existing data-driven approaches do not account for these uncertainties and lack of interpretability. The widely utilized method is the Monte Carlo sampling-based technique, which obtains the load margin distribution via a large number of continuation power flow calculations. From the calculation process of CPF, it can be seen that CPF involves tensor power flow calculations. As a result, MCF is time-consuming. To reduce computations, we propose to construct a data-driven, computationally cheap probabilistic surrogate model to replace the CPF module for load margin assessment. Specifically, to obtain a comprehensive dataset for training the surrogate model, here is the deep kernel learning. Active power of wind generations, real and reactive power of loads are sampled from their corresponding probabilistic distributions. However, the exact probabilistic distribution of these uncertain sources may be unknown, since only historical data is provided. Therefore, we employ C1 coupler to construct the joint probabilistic distributions from the historical data. Based on the inverse joint probabilistic distributions, active power of wind generations and the real and reactive power of loads can be sampled by MCS. As a result, corresponding load margin can be calculated by CPF. Therefore, DKL can be trained with the dataset, while active power of wind generations, active power of synchronous generations, as well as active power and reactive power of loads are as input, and corresponding load margin are as outputs. Once the surrogate model is trained, we can use kernel shape to identify the critical factors that affect load margin for preventive control. From this figure, we can find that coupler can capture the distribution of wind power and loads efficiently. This allows generating more representative data for machine learning algorithms. For the surrogate model, DKO merges the deep neural network and Gaussian process regression. This leads to a good capacity of nonlinear representation extraction and less requirement of training samples. From the figure, DKL utilizes DNN as the feature extractor, while Gaussian process can make efficient uncertainty quantification for load margin. Therefore, DKL's loss function is trying to maximize the log marginal likelihood like Gaussian process. To verify the proposed method, numerical simulations are performed on the IEEE 118 bus power system. We take support vector regression, GPE, DNN at comparisons with the proposed method. Generators at bus 1, 4, 6, 8, 10, 12, 15, and 18 are replaced with wind generations with the same rated power. All wind speeds obey Weibo distributions. All loads obey normal distribution. It can be observed that although the non-parametric method GPE requires the least number of samples, its accuracy is not satisfactory compared with the DKL and DNN. DKL and DNN outperform both GPE and SVR regarding to the prediction accuracy. Basically, GPE and SVR do not work well at the summit and the tail of the load margin distribution, while the latter is especially critical for voltage stability analysis. On the other hand, DKL requires much less samples than DNN due to its strong Bayesian inference capability. Once DKL is trained, its result can be interpreted by kernel shape. We can see the calculated Shapley value by kernel shape as a kind of sensitivity. According to this sensitivity analysis, to get a large load margin, we can keep the active power at bus 10 larger than 3 per unit. Increasing generation at bus 59, 62, and 100 will also lead to decrease of load margin. Finally, we can come to the conclusions. We found that the proposed method is able to perform accurate PLMA with fewer number of historical data requirements as compared to the other deep learning approaches. The proposed method provides useful information for system operators for corrective controls for system voltage stability improvement. In the future, we will develop transfer learning approaches to enhance its capability for handling the topology change and capacitor control actions. And also, we will develop Shapley value-informed preventive control approaches to improve the load margin. This is all my presentation. Thank you.